Okay, hello everyone, and thanks for attending my talk. I'm Valentin from ThinkCell, and today we will talk about text formatting and how ranges may help you with this. So text formatting is one of the fundamental problems in computer science. Like, not only that we have to present text to the user, we also have to deal with text-based file formats like JSON, XML, HTML. And so there's already many libraries that kind of deal with text formatting. And our idea here was basically, let's just take what we like and try to build something really cool. So probably that hopefully everyone will be using it, or maybe not. So, so what's the task we have here? So we are having some components we want to print as text, and we also want to be able to print them in some particular order. And sometimes you also need additional parameters to specify. We want to supply additional parameters to specify how, for example, to print a number, how many decimal digits to use. And as output, we want some string of characters. So currently, if we look at the current state of art in C++, there's basically two things we can do. Either we use format strings, like we have these strings with these placeholder tokens that tell you where to insert your text components, and also the placeholder tokens also may have some funky syntax to encode how many digits you want to print with your number. So there's printf, I think everyone knows printf, and then there's also the lazily library that basically follows the same approach. And in the end, we may get in C++ 20 the std format library, which uses Python-like syntax for formatting. And then we have, as an alternative, we could just try to do it in C++ only. So we have a string stream, or more generally an I stream, where we just shift in all our parameters and all our components, and then they will end up in a string. And we can also do, we try to concatenate strings, and that's also another way to just do it in C++ without any format strings. So I want to look at both variants and just see what's good about them and maybe what's not so good about them. So, so the good thing about format strings is that they are a little bit like what you see is what you get. So if you look at a format string, you can already get a preview of what your string will look like. And another good thing about format strings is that we can supply the format string at runtime. We do not have to supply it at compile time. So think if we get it out of a translation library or something like that. And if we do that, the downside is obviously that we don't have any compile time checks. If we supply the string at runtime, we cannot have the compiler check the list of parameters against, or the list of arguments against the format string itself. And on the negative side, of course, we have to do escaping. We need to be careful to escape every time if we, for example, use a percentage sign in the printf syntax. And we must not forget to do this. Also, we have this funky extra language to specify the parameters, like how many decimal digits you want in your number. And I think my microphone is just slipping. Someone can come up here and fix it. But you have this extra language or extra special magic syntax to specify your parameters, and we would certainly rather prefer C++-like syntax there. And also, they are very hard. These format string libraries are often very hard to basically specialize for you, customize for your own types. So with some formatting, it's not possible at all. With other libraries, they allow you to basically write your own parsers to get your arguments there. You need to implement your own parsers to extend this, and that's not seriously what I want to do. And then you also, it's like you have no gradual change when going from string concatenation to formatting. So if you want to concatenate two strings, you probably wouldn't use a format string to do that. You can just concatenate two strings. And if you want a number in the middle, then basically what you end up is with a format string that looks completely different, or you somehow have to take it apart and factor it out in kind of a temporary solution that creates the number and then appends it to the string or something like that. So there's, however, one thing where you absolutely need to use format strings, and that's when you do internationalization. So we are just a company of 40 people, so we cannot do the translation in-house. We have to outsource it to some agency. And usually you don't want to give these agencies access to your code base. You don't go there and say, just change all the code to Japanese and then check it into Git. You rather exchange text files with them. And what you, of course, need to have is placeholders. And so you must have some support for these placeholders. But you always have to remember that these people working in these translation agencies, they're usually not computer scientists, so you don't want them to mess around too much with complicated format strings. So you don't want to give them more control than necessary. So certainly they have to specify where to insert the text, where the text should be inserted, in which order the placeholders should appear. But other than that, you don't want to give them any further control. So yes, you may ask, what about number formats, for example, like what kind of decimal separator you want to use? Well, the answer is quite easy. You don't need, the translators don't really need to be concerned about that, because if you are just taking your language from the regional settings, you can as well just take these format settings from there and just do it all in your code by having the right, if you have the right tools available. Also, there's stuff like the number of decimal places that usually, or in many cases, doesn't even so much depend on the language that you're translating into, but it's kind of a thing that depends on the context where you're printing numbers. And then you may have languages like US English, or you may have, you want to sell your product in the UK, and they are both using the same English strings, but still you have to somehow switch the date format from month, day, year to day, month, year. So basically, our take on this is we just give the agencies control over placeholder positions and do everything outside of the format string. Then we have the C++ side. So we can use string stream. And in my opinion, string stream is so terrible that I didn't list any pros here on the slide. I just listed cons. So first of all, you may consider this an abuse of operator overloading, which is basically, well, back then in '95, they needed a way to basically pass an arbitrary number of parameters into a string stream. Today we could use variadic templates to do the same without operator overloading. Then if you want to set a format, you do this using stateful manipulators. So you just set your precision and then you do print your number, and then somehow if you have to reset it later inside your expression, and it's kind of messy. And I know many people think that's not a bug, that's a feature of I/O streams. But then if that's a feature, why does, for example, width only apply to the next item? So it's kind of a mess. And then in the end, they are also, I/O streams are also very slow. And that's kind of surprising, because you would expect that they are actually faster than printf, because you don't have to pass a format string. But still, it's the way they are implemented currently, using all these stateful manipulators and using the way the I/O stream talks to the I/O buffer in the background. It's kind of implemented in a way that it's actually slower than printf, which is also a little bit annoying. And if you have to get your string out in the end, you have to take an additional copy. You have to copy the string stream buffer if you want to have it in a std string. So what about concatenating strings? So it's also using operator overloading, but at least there it's not that bad, because at least you stay in the same domain somehow. And you currently have only limited options for formatting, so we have std to string, and that's pretty much it. And if you do it like that and you're concatenating many strings like that, it will be horribly slow, because every time you concatenate a string basically means that you're creating a new temporary, and then all the buffer will be copied over, and then you concatenate the next string, and the same thing will happen again and again and again. So you're wasting a lot of time just allocating memory, copying memory. But in a sense, it's still close to our input setting, where you actually have data snippets, you just concatenate them to form a string. And also you can extend this, like with that is the to string, you could also add another function that somehow generates you a different string with a different format. So it's extensible. So can we maybe have something similar to this that's okay, operator overloading we can easily get rid of, but that works in a similar way but doesn't have the shortcoming of std string-based concatenation. And yes, the answer is the new standard will have ranges, and maybe we can use that. So just a quick recap on ranges. How many of you know the range-based for loop? I think most of you. Who knows the ranges as they will likely appear in the C++ 20 standard? Yes, many people here, that's good. Anyone has been working with Eric Niebler's range v3 library, which is kind of a superset of std ranges? little bit. And most importantly, who is using ranges in their software development every day? So with and this, whatever, if it's Eric's library or the Thinkcell library or Boost or something else. So I would really strongly suggest just to look at this and do so, because I think so that's kind of the one thing that had the most impact on how we program, and it leads to more canonical code. Like if you're using ranges, you're basically having users write code in a similar way, and it gets more readable and more self-explanatory in my experience. So just have a look and try to do that. So what's a range? In a nutshell, a range is just something with a sequence of elements. And in C++, we are using iterators. So to encode a sequence of elements in C++, traditionally what we do is we have a begin iterator and an end iterator, and then that's kind of a range we can use. And then we can run algorithms from the STL on it, like std_find, for example. And that's a little bit cumbersome because you always have these two iterator objects, and it makes it really hard for composition. So if you want to compose algorithms and you always have to deal with pairs of iterators, it's kind of messy. So the idea was, why not just put it all simply in one object, and that's a range, and then you can run your algorithm on the single object applied to a single range. So a range in terms of the C++20 standard is anything with begin and end that somehow gives you meaningful things to iterate with. Could be iterators. We also have concepts of Sentinel later. And obviously that includes all the containers like vector, basic strings. But you could also have views that don't actually own elements, that just reference elements that are externally in some other containers. And in particular, the one thing that's very useful in ranges is that you have these views that do lazy calculations. For example, you may apply a filter to any range, and then you get a new range that is basically the filtered version of the original range. And this is lazy, so if you just write that down, that wouldn't do any filtering at all. So it only starts skipping elements over elements if you're actually starting to iterate over the sequence. So at Thinkcell, we have been adopting ranges more than a decade ago. We have been excessively using boost ranges. And then later, when we just encountered some shortcomings, we have gradually started developing it out into our own library, which you also may find on GitHub. And we are heavily using it everywhere in the production code. So we are having more than 1 million lines of code to actually use it. And that's also very important, because if you design any kind of libraries, in my opinion, you can't do it on a paper. So if you just sit down on a paper and try to come up with a good library design, and you haven't used it yet, you don't really know if your approach fails. And you really have to just implement it and see how far you can get and where the limitations are. So what kind of problems you can't solve. So you have to use it, but once you have it out there and using it everywhere, then kind of, well, people are reluctant to change the library because there's so many lines of code, and if we make a fundamental change, then we'll suddenly break everything, and people are afraid of doing that. So how we approach this, basically we have both the library and the code in-house. So whenever we try to change something in the library, we can simply go through the code and basically look at all the use cases and see how they would be affected. Of course, this means that you have to dedicate the resources to do so. So maybe not every software company is willing to do that, to actually pay people for doing refactoring for syntactic sugar reasons. But let's get back to text formatting. So a text is just a sequence of characters, so it's very likely that, or it seems like a very natural thing to work with ranges. So we have, for example, std_string. Let's just see what we can do. String is already a range. So we can, for example, instead of using the string member interface, we can just run the range algorithms on the std_string. And that's nice because, first of all, you only need to learn one set of algorithms. You don't need to learn a std_string interface, an interface for another container, and you can just have a set of tools that kind of work almost everywhere. And also, it's important if you need to wrap system-specific types, like say you're on the Mac and you need to wrap CF string, or you're on Windows COM programming, you need to wrap the B string, then well, all you need to do to make it work with ranges is basically you just need to implement a simple wrapper that implements begin and end and gives you kind of 2 pointers. And that's super easy to do. So you are not, because you separated the algorithms from the actual container, you're not having to re-implement the entire std_string interface. and you can all use the same syntax and exchange data types. Well, in C++17, I think most people of you know that. We have a similar approach. We have this basic string view. And that's kind of nice because it's kind of one of these adapter wrappers that adapts to everything. But the downside is, in my opinion also, and your opinion may vary, is that that somehow proliferates this old string interface even further. So let's see what else do we have. We can concatenate strings using the range library. So virtually every range library out there has a concat function. You just give some component ranges and you combine them in a new range. You can also kind of do formatting if you add formatters that return a range of characters. So in the public library, for example, you'll find functions like tcsstack or functions like tcshex that will take a number and some additional parameters and then turn it into a character range. And then you can concat with that. And this is this is a quite clean separation between formatting and concatenation. So it's unlike the IO stream where you basically somehow have one tool trying to do it all, doing the formatting, doing the concatenation. So the formatting just takes place in the TCS stack, and the concatenator doesn't know anything about formatting and doesn't need to know that. So if you try to actually concatenate a string with a number and try to use that as a range of characters, that just simply won't compile. So you don't need any specific format function inside the concat itself. And we can extend this if we want to create more complicated formatters based on what we already have. Could, for example, have a dollars function that basically prints a number using 2 digits, appends the dollar string using concat, and returns that as a range of characters from a function. Then we can just use it all over the place. And as it's a range, we can just use for each. For example, you can just iterate it to get the text out. Or if you, for some reason, like, you can also run any other range algorithm like all of, any of. Maybe more importantly, you may want to filter or transform the text ranges, as usually. So now that we can do that, we also need to be able to construct a string out of it. So say we are working with our famous favorite UI library, and this only accepts some kind of string. So you need to be able to construct a string from a range. It's kind of the other way around. Before we were constructing ranges from strings, and now we need to go back to the string. And we would like to be able to construct a string from a range. So what do we have in the standard? So we can construct the empty string. We also can construct a string from a string, or we can construct a string from a string literal. And hopefully a future standard will also eventually, now that ranges are standardized, give us a constructor that accepts a range as an input. So you can construct a string from a range, either a single range, or you can use your concat function to concatenate many components. And as you use that very often in your code, it would be nice if you would be able to just omit the concat there and just basically, because we have variadic parameters, we can just variadic templates, we could just also get this to work, like just passing in many ranges, and then they all will be formatted into the container. And well, this may, of course, conflict with other constructors that we have in string that have multiple arguments. So let's see what they do and how important that is. So what the first constructor that is doing, the first example is, well, it will construct a string by copying the first 3 characters from the string literal A, which is buffer overrun. So this is probably not very useful. The second example is a little bit more useful because it will add 65 times Control-C into the string. But I think what the user really wanted to say here, most likely, he just wanted to have a string which contains the character A 3 times. And I'm not really sure if these constructors are so useful anymore. In particular, if you have ranges, you can just use your repeat n function from your favorite range library that you're using, if it's Eric's library or something else, and just say what you mean. And if you repeat n and you get the ordering of the arguments wrong, you just end up with a sequence of integers, and that just simply won't compile, so it's quite safe. So now, sadly, we cannot change the STL. We want to use the code today. So what we have in generic code is we have this explicit cast feature, which basically by default constructs the target type from its arguments. And using the auto syntax, you can also write it in a way that you only mention the type once. And well, we also overloaded to simulate constructors that we don't yet have in the libraries. So if you're using the Thingsel library, these examples here that you see on the screen, they will just work. And we're using this explicit cast also in the generic library. So for example, having a tool like content place back, which fills a vector of strings with whatever you give it, then this example here, we just pass a range, also works because it internally will use explicit cast to construct the string when placing it. And sometimes we also have the use case where we only want to append to a string, and we don't want to construct a new string. We have a string, we want to append some characters. And there's also an append function which appends one range or any number of ranges to an existing string. Of course, if we deal with internationalization, or if you like it more, we can also have these placeholder strings. So we have TCS placeholders, and they just plug in the range that you give as arguments where the placeholder is, and then returns another range of characters. And what you then can do, and that's, for example, a very important nice feature, is that you then give the resulting, take the resulting range and just run it through an HTML escaper. That's also very useful. You may concatenate it with more HTML code. You also have named args if you need that. If you have longer format strings, sometimes it's nice to have named arguments. And what's important to notice here is that there's once again this clean separation between formatting and the placeholders itself. So the placeholders also just accepts any range that you give it. The placeholder doesn't, TCS placeholders doesn't by itself do any kind of number formatting. So you just do that outside using C++ syntax. Can format numbers and dates. So we've seen so far to the side how you can use ranges to do such a thing, using our library, for example. And now I want to talk a little bit about how to implement that. So, of course, you could prototype this quite quickly. You could have these formatters like TCS stack, TCS hex, just returning strings. And then you could have a version of concat that takes two strings and just concatenates them using string addition, or append to implement append in the same way. But of course, I mean, that would be simple. But the downside is you would have this terrible runtime because you will end up with a lot of temporaries and copying and everything. And also, the talk would be over now. So the idea here is to make it faster. Is basically, first of all, we need to get rid of unnecessarily heap allocations. So we can do that. We are working with ranges, so why not just making these kind of ranges lazy? We can basically have all the formatters that we have to use lazy evaluation to just not generate the character string up front. And if you do that, you of course still need some state inside your formatters. For example, if you have a stack, you need to remember the parameters you just gave it. But that's kind of, you all have that at compile time. So you can completely just have an object that is on the stack and that just doesn't need any heap allocations. But if we go to the example where we have our custom formatter that returns dollars, so what would that return? So first of all, you run TCS stack. And TCS stack will give you basically something that stores the input parameter, and it will store the number of decimal digits in this case too. And then you're using concat, and concat will internally store the component arguments. And what we do is that if the component argument itself is an L value, then we're just basically concat just stores a view. That means we're just storing a reference basically. And if you pass in temporary, we will aggregate whatever you give it to it. We will just aggregate it internally. So that's a very nice feature that we use throughout our entire range library. It's not only specific to concat. And by doing so, you don't have to deal with so much with annoying lifetime problems. You can just inline your expressions, and then you don't end up with dangling references like in a way like Nikolai described this morning in his talk. And in the end, you end up with some kind of object tree on the stack. And it's very much like expression templates. So once you start iterating it, then you just reverse the tree and just generate the characters. So this way we can go completely without heap allocations for these examples. So of course, if you want to output this entire formatted string in some way in some container, like you need a std string, you need to do a heap allocation, obviously. But even then, there's this kind of textbook approach that we first have to determine the string length, then we do one allocation, and then we copy in the characters. In a way, std string already does that, or the standard containers already do that if you use the constructor that takes 2 iterators. But it's not quite optimal, because what actually happens if you use that is that typically you have formatters which don't offer random access iterators because it's too hard to implement, or maybe it's not possible at all. So what std string then will do, it will use the distance to determine the string's length, which will mean if you have something like a string that's several kilobytes or megabytes large, it will iterate it once. It will basically generate the entire string once, just to determine the string length. And then it will generate the entire string a second time to copy it over. So obviously, std string can't do better because std string only sees iterators. It doesn't know anything else about the range. So what we can do if we have the range, we can, in many cases where we don't offer random access, we can still implement a size function that's either very efficient or at least much faster than generating the actual character sequence. And what we want to have is basically that the construction of the string takes advantage of the size using std size, and basically to determine the size of the buffer. And yes, it would be easy if we could just do this inside the STL directly, but sadly we can't. So we have this explicit cast feature, and for creating a string out of, or any container out of a range, it would then look like this. You just take a container, you call reserve on the container, and then you are having this loop that copies everything over. Then you're returning the container. The same you can do if you are appending to a string. You have the container size, and then you add it to the size of the new string, and then you're doing the copying. And this way, at least you don't need any further reallocation while copying the string. So is this any good? Well, actually, it's quite stupid to do this way, honestly. Because if you're doing append and you're having use cases for append, you'll probably append a second time and a third time. And the problem with cont reserve there is that it basically does exactly what you tell it to do. So if you just need to add one more character, you're just saying, OK, let's reallocate and let's just reserve one more character and copy everything over. And then you put in the next character and the next character, the next character, the next character, and every time you plug in and append another character, basically it will reallocate the entire string. So what we should use there is some tool, like we have cont reserve, that actually tries to grow the container geometrically. So that way, if you do that, then you are guaranteed that whatever kind of sequence you have, of append sequence you have to add in total n characters, you are guaranteed that you only copied a linear amount of memory and that you only did logarithmically many memory allocations. So now we have kind of optimized the heap optimizations away, or we at least minimized the number of heap optimizations for appending strings. And there's yet another very serious bottleneck in this program. So if you see, when we copy over the string, what we're using is a for loop, and that for loop will use iterators. And that can really have a terrible performance, in particular in the range setting. So why is that? So consider we have a concat. We're concatenating ranges. So we are dealing with different type of input ranges. So basically what you have to use to build an iterator that works for a concat range is we need to use some variant, either std variant or something we internally build. But however you do it, you somehow have to switch inside your code whenever you dereference the iterator. Whenever you increment the iterator, you need this additional switch. Am I in the first range, second range, third range? And then you need to branch on that. Then second, if you're iterating the first range, you must always internally, every time you increment the iterator, you must check internally if you're reaching the end of your first range. So you switch to the second range. And so you have this additional end check internally every time you call ++. So the outer loop will check end, and then you call ++, and then the inner loop will also check for the end of the inner ranges. And if you do a concat of a concat of a concat of a concat of a concat, you see where this leads to. Kind of complexity explodes. So there's a reason why this, also with a stack, we can have some iterator bookkeeping, but maybe that's not that important here. The reason why it is like that is that C++ iterators, basically, if you use C++ iterators, you do external iteration. That means you have a consumer, and every time the consumer needs a new element from the producer, it will simply call the producer and say, give me the next element. It's kind of the simplified model here. And that means that the consumer is always at the bottom of the stack and the producer is at the top of the stack. So this is very good if you are the one who has to implement the consumer, because you can just have one code path that iterates the entire range. This is much easier to do because you simply could write any loop or any kind of sequence of instruction to do so, to consume your elements. And also, you don't need any external state to tell you where you are in your computation. You just have the instruction pointer that's basically encodes the position where you are in your computation, and you have the control over the stack. Between getting two elements, you could call into a different function and recurse as much as you like, or put different things on the stack. So that's kind of gives you very good performance if you're implementing consumer. But for the producer, it's kind of disadvantages. So you only have a contiguous code path for a single item, which means once you return that item, you're off the stack. So you can't use the stack to just store additional state or data. You just have to keep it around in your, if you're a producer, you have to keep it around in your own state, in your own object. And if that's not constant size, you basically can't do anything. You have to go to the heap. So when the STL was designed 25 years ago, that basically was a wise decision to use support external iteration, because back then the use case was we have simple iterators that just iterate over simple collections like vector or map, and we may have to do all the hard work inside the consumer. So that's basically why back then this external iteration thing using iterators was a very good idea. But if we're doing text formatting, the situation is kind of the other way around. We may do very complex things when we generate the text. Like we could, for example, generate entire websites with a lot of data in it. And yeah, we rather like to do that using internal iteration. And then the consumer is often very trivial because it just needs to append something to a string or to put it into a file or something. It's usually much more simple than the producing part. So we can just switch it around. There we have the producer, and it calls the consumer every time it has a new element. And the producer is at the bottom of the stack, and the consumer is at the top of the stack. And basically, the situation is exactly the other way around. So the question is now, we are having a range library. And a range library is currently using iterators, or similar concepts to iterators. So can we make that all work with internal iteration? Well, there's obviously certain things you can't do in this model. Like you cannot do binary search. You need random access. It won't work by just having someone giving you elements one by one. Also hard to implement something like find, kind of, if it needs to return an iterator, because you're not using any iterators. But if you're implementing find algorithms that like find if, that just you look for an element that matches, you can, at least if you are okay with getting the value instead of an iterator, you can do that. And then there's other range algorithms. So we have for each, which trivially works because essentially if you're doing internal iteration, you're basically having for each. That's kind of what for each does. It just calls the functor with every element. You can implement stuff like accumulate, all of, any of, none of quite easily using internal iteration. And also you can implement range adapters like filters or transform. You can just basically implement wrappers around your consumers that then will do the filtering and the transform internally. So kind of you can implement that all. You just need to do a lot of programming to make it look syntactically similar. So let's extend the range concept to internal iteration. And what we do in our library is basically, so we're saying a range is everything that implements begin and end. That's still true. But in addition, we say also a range can be anything that implements a call operator where you can just pass a sync functor that expects your elements. So why didn't we use a named function there? Why did we use the call operator? There's one particular reason where this is very useful, and that's so you can just basically write ranges as lambdas. It's very useful in particular if you need just return a lambda from somewhere and you just have a range that you can use. So in this example, we have a range that basically just generates the elements 1 and 2. And then we can run for each with it, or we could also apply a filter and transform to this, and it would just syntactically look the same as with a if you are using vector or some other classical range, and it just works. So if your range implements both, we will always use internal iteration, because the assumption is that it's very unlikely that there's anything that where external iteration is going to be faster than internal iteration. And if it's not available, then it will just use iterators. And of course, you need to be a little bit careful. You must take care to finding out things like span, which implements also a call operator which accepts indices. So you really have to make sure that you have no false positives when you're compiling things. Okay, can you use a call operator there? And it's not really what you want. So if we are having internal iteration, we can implement concat in a different way. So now basically, our concat range basically has this call operator that accepts a sync functor, and then it will use a for each to iterate over the tuple. And that's kind of syntactical sugar we have here, iterating over a tuple using for each. And it's a kind of nice feature, but it's not, you have to understand that this is not kind of a runtime loop, because the tuple holds different kind of types. It's just unrolled at compile time, and we'll call the inner functor with every object inside the tuple. And then you have the inner loop that basically uses for each again and applies the sync to the range. And that will also use internal iteration. So that's, if you unroll all this and the compiler is doing the inline, this has no overhead compared to the handwritten for loop that we would do to concatenate different ranges. So what if we want to append into a string or convert into a string? Then we need to have a sync that basically appends elements. So we can do that. We can write our TC append in a way that it calls for each on a range and then basically uses an appender sync. And the appender sync is, you can customize it for certain target types. Sometimes you can implement clever implementations. Maybe see some of this later. But we also have this default that works on standard containers that just uses mplaceback to append to a container. So there's obviously one thing that's missing here if we have the appender sync, and that's the reserve, the call to reserve, the memory allocation. So how do we do that? So in order to get that right, we need to be able to somehow show the sync the entire range before we actually run the iteration. So we also have a customization point named chunk, and if you have a sync that also implements chunk, then the range library, or for each, or also other range algorithms that you internally use for each, will call this chunk method first and pass it the range. So the chunk implementation for the appender can then just reserve the memory required in the container, using the reserve member function, but using this geometrically growing reserve function. And then we do the for each for the internal iteration and just basically use the appender that just uses mplaceback. So that's how it works. And this chunk method, it seems like it's kind of an ugly hack because we somehow need to reserve memory, but it also has other use cases. For example, if you're formatting into a file, if you have an appender that appends to a file, and kind of you can say, okay, if my source that I have, my text that I get offered is already some kind of contiguous memory region, so then I don't need to, in any way, to copy the characters over and store them in any path. I can just immediately write it into my file. I can just immediately use fwrite. And if you have a concat range that consists of ranges of different types, then this chunk will not apply. But then the framework, when doing the internal iteration inside the concat, it will eventually at least use the optimized chunk function for all parts in your string that are just string literals. So even if you just have a huge HTML file and there's a single number, at least, I mean, it does then do the single number in a special way. That's maybe not optimal, but for all the string literals you have in there, you benefit from the chunk function. So it's actually kind of a useful tool there to have. Also, if you are formatting into some other buffer, you can say, do in certain circumstances, do unchecked writes into your buffer, or using memcopy if you have contiguous memory regions. So it's kind of a nice customization points for optimization of all kind. So now there's this question, are we using kind of this range library? And question is, actually how good is this in practice? So how much are we really using? Obviously, it's not like handwritten assembly or something, but how much does it cost us to use a range framework? So what we have here for benchmark is basically we have a trivial formatting task. So we're having a string, and we're trying to write 10 times A into the string, then 10 times B, then 10 times C. And the reason why we have this trivial formatting task is because what we want to measure in this benchmark is really what kind of overhead we create in the framework, in the ranges framework. We don't want to measure the overhead in the decimal number formatters or something, because that's something that you can get externally that you usually don't write yourself. We also don't want to benchmark the performance of std string. We really want to know if we're using the range framework compared to a handwritten loop, what are we actually using? So we have this handwritten code that basically has 3 loops. So at first it just writes 10 times A to the buffer one by one, then it writes 10 times B to the buffer, then 10 times C. And then we do it using ranges. So we are not writing to a string here, we are just writing to memory buffer. So we have this simple appender, which just has the buffer. And every time the appender thing just receives a character, it just puts it at the end of the buffer and then increments the pointer by 1. So next character will end up in the next space. And we are using the range framework. We're saying tc append to the buffer, which will use the appender that we have there. And we're using repeat n to basically say, OK, n times A, n times B, n times C. So the outcome here is that if we have this iterator-based range algorithm that uses external iteration, it's already 50% slower than handwritten code, which is still kind of OK. But if you're doing concat, then you could get some problems. If we're using the version that does internal iteration, however, it's only 15% slower than the handwritten loop, which is, yes, you could still argue it's not kind of like handwritten, but still, I mean, you're using a complex range framework that's very powerful, and that's a very low price to pay for it, in particular if you compare it to the iterator-based version. And here we only had a very trivial use case. So if you're actually generating real data, so like you have to scavenge your string somewhere from some translation library, and you have to format numbers, and you have to put it into a string or into a file, I mean, you have much more overhead there. So kind of, if you have real world use cases, the difference, the price you pay probably is much smaller than that. There's another final benchmark I want to show you, and that's about this custom appender customization point. So how could we benefit from writing custom appenders that are optimized for certain containers? So to do that, we just recreated a basic string implementations, and we left out the small buffer optimization for simplicity. It's kind of cheating, I know. And so the string implementation just has 3 pointers. There's a begin pointer that points to the begin of the allocated region. It has an end pointer that points 1 past the last character in the string. And it has an end of memory pointer that tells you where the allocated region ends, so you can check for buffer overruns and then do the reallocation. And once again, we're doing the same trivial task. We're writing 10 times A, 10 times B, 10 times C. And we're using basically the range algorithm we have before. We're just saying tc append with tc repeat n. So then if you just write this, first use the standard appender if you don't have a customized appender for this type of string. And just as a recap, it would look like that. You have this inner appender that just uses mplace back to just mplace your characters. And you're having the chunk version that then does the reserve and then basically runs the internal iteration on the inner appender, which does the mplace back. But that's in this case, if you're writing to the string, it's not quite optimal, because what happens if you call mplace back on a string or push back is basically that every time you do that, it has to check if you would overrun your buffer and if it needs to reallocate. So it does these kind of check writes. It will check, have you reached the end of your buffer, and do I need to reallocate? But here, as we already reserved the memory, we know that there's enough memory. So what we can actually do is using unchecked writes into the buffer. We're just writing into the buffer, and we don't do the check for the end of the allocated region. So this obviously saves some time and also shows in the benchmarks. Here, the benchmarks included a heap allocation, which is by itself quite expensive. And even though this had this heap allocation, the custom appender still was 20% faster. Just basically that means that the default way of just pushing characters into a string wasted 20% of the time by just checking for the end if you have reached the end of the buffer. And we would like to do something with the SL containers, but unfortunately they don't expose their uninitialized buffers. So you cannot, it's kind of clear they don't want you to mess around with it. But if you're using the STL without patching it, you sadly cannot do this. So you have to basically write your own basic string implementation if you want to benefit from that. So much about performance. Now there's maybe some future work that we can do. So most cases we have a size, but sometimes don't have a size, so we may have estimates. Like we, for example, may have a minimum size that a range could have. And if you don't have that, you could just default that to 0. And then if you use that for allocating memory and you can use min size, then basically if you didn't implement min size, then at least you know that this isn't going to be any slower than it was before, because it just returns null and then will not reserve any memory up front. But sometimes you have pretty good estimates, and then you can sum it up over concat. Also, you can do the other thing, if you can implement a max size. So why would that be useful? So consider you having a file appender. So you're not appending to a container, you're appending into a file. And it's not using std file, it's just basically implemented on top of the operating system. And when you do that, you need to do some internal buffering. So you cannot basically just do a system call for every character that you write. That's kind of waste. So you would like to do some buffering without going to the system. And typically you have this pre-allocated buffer that has a certain size. And what you can do is, if you get a range and you should append it to a file, you can basically check what's the maximum size this range will have. And then you can check what's the maximum size I have at the end of my buffer. So and if you say you have, the range is going to be 300 characters, but this range buffer still has 1K left, so you can just use unchecked writes or anything else to basically fill the buffer quickly, and you don't have to check if you have reached the end of the buffer and you need to flush it. And the same is obviously also true when having custom appenders working on things like strings, where you can also do unchecked writes, given that you have a string implementation under your control where you actually have access to the uninitialized buffer. So that's also something you could do. So what have we seen in this talk? So first of all, if we need text formatting, we can use ranges and C++ syntax for doing the text formatting. If we want to do this more efficiently, we need some customization points in the range library. The most important is probably internal iterations. And also we have then this need, if we do that, we also need something like the chunk customization point for memory allocations. And if we do that then the performance can be competitive with handwritten code. So if you want to check that out, you can basically go to our GitHub repository, check out the range library. Everything you've seen in this talk, except for the future work, is already in there, and much more. And if you're interested, we're also hiring new developers, and you can also apply to the company if you rather prefer to develop this in-house. So that's it for today, and now we still have some time for questions.
Hello, and thank you so much for your talk. Don't you think that the ranges concept is an overkill for text formatting? What I mean is that usually you have some really big text that you want to fill with your data, and it's a single template, and you can use any of the other frameworks like Jinja, CPP, just to fill it. And it can be lazy too. I mean that it can fill data on the fly while you read from it. So why actually should we use ranges here? Thank you.
So as far as if I understand it correctly, you say you usually, the question was why use ranges when we have also other things that we can use, and in particular when we can have templates where we just basically fill in the text, right?
Yep, usually have, as far as I understood, you have some template that you want to fill with data, and basically have other more simpler concepts to fill it with it, and without so much so much performance degradation.
So your templates, you mean like your text templates, and then you have kind of placeholders, or maybe? Yeah, I mean you can also do that with our library. So we also have something where you actually can instead of having placeholders, you can basically match any substring inside your template and inject your ranges there. And then there's the question, well, why do we have to do this with ranges? So the answer is kind of simple, because we have this range library that's powerful, and we can just do it. So if you prefer something else for whatever reason, of course that's also okay. But that's usually that ranges are not for text formatting initially. But it turns out that ranges are quite useful if you actually also need this in your program, and then you just use ranges. That's rather the point I want to make. It's not like there could be other solutions that also could do it in the same way or the same performance. It's rather like why do we need so many tools if the tools we already have already work? And all these kind of optimizations I just showed you, like using internal iteration, it's not just for text formatting. It's you kind of, if you have that, you start benefiting from it anywhere. It's kind of rather that somehow you, if you have already tools available that can do a good job. And we are basically, we have our web server that generates a lot of data. We are generating file formats. We are generating internal data for PowerPoint and all that. When we can all that using this framework. Of course, we need some more functionality than I showed you, because sometimes you have more complex tasks for formatting. But it just works, and we don't need to come up with yet another solution for text. That's rather the point I would like to make. So.
Okay, thank you.
There's another one.
It's like your computer is going to sleep right now.
Hi. I have a question. Have you tried using, instead of this internal iteration that you used, to try using coroutines and generators?
That's a very good point. That's a very good point. So I explicitly omitted that. So there's internal iteration, there's external iteration, and then there's coroutines. And coroutines are kind of interleaved computation. So you just simply have two different stacks. Yes, and in a way that's very interesting. And now we got a coroutine proposal in the standard that's kind of mostly through now, and there's a downside because it's stackless coroutines, and basically we try to use them also in the context of the stuff we do with ranges, and we had this one point that we really didn't like, that they are kind of infectious, and the way we program with all this kind of lambdas is kind of, if you have a lambda that somehow internally deeps inside that needs to yield, then basically you need to turn your entire framework into a coroutine, which basically means you have to annotate your code twice, and it's kind of really hard to do. In general, if we have coroutines, I mean, you could really have producers that use coroutines. And then there's also the question about the performance, and yeah, once we have something that we can really use, we can try it out. So currently we are really doing it without coroutines. But obviously, coroutines is also kind of a solution to this problem, that you don't want to produce your data inside of some weird iterator with some weird state. So,
thank you.
Thanks a lot. First question: how? As I've understood, your example with a dollar is the example of extensions of types. Am I right?
I'm not sure if I understood the question.
Maybe
maybe you just take the mic closer to. Thank you.
I'd like to print my types, and how can I do it with your library?
Well, basically you can just use. Basically, it depends on the type. So if your type is basically something like a matrix that print numbers, then just do it like that. Then just write a function that iterates over your matrix and prints numbers. If you have something more complicated that doesn't easily translate to numbers, then of course you need to think about how to format that. But that's kind of the same problem you also have with format strings that just support numbers. And what in particular do you have in mind? For example, if you have a structure and you want to print that, then yes, then you can create for example, a formatter that will print all the members, which obviously today, if you don't use tuples, it needs introspection, which you don't really have yet in C++. But
I see. And the next question, you use a procedure style. Have you tried to use the classes?
if we have tried to use, we have used, can you tell?
All your library use the external procedure style. Have you tried to use the classes style? Use the classes.
Use the. Sorry, I didn't understand. Use. So we are using structures and not classes. So that's what you're asking for.
Thanks.
We can discuss it later, maybe.